Hey, friends in industry, it's time to start the second part of our today's expert talk. We are now at GaN, and the way we proceed is that the presenter always gives a short summary of his article, which was once published in the magazine. And then later on, we have the cross discussions. And the moderation is now taken over by Alfred. And I will relax, sit back, and watch.
Okay. Hello, everybody. Welcome. My name is Alfred Vollmer. I'm editor-in-chief of Bodo's Power Systems, and I'm very glad that you came here to join us for our gallium nitride session. I see that both of our presenters will be here. I suggest that we will start with EPC, with Alejandro. Do I pronounce your name correctly? Oh, you're still on mute, Alejandro?
You need to turn on.
Okay, very good.
Yes.
So I'd like to turn over already very soon the microphone and the video screen to you, because you provided a three-story series about increasing power density using low voltage GaN FETs in high voltage server power supplies. Please give us a short overview what you wrote in this three-part series. And before I hand over, I'd like to encourage everybody here in the audience to ask the question you always wanted to ask and write them into the chat, please. We will then read them for everybody. Alejandro, now it's up to you. Thank you.
Thank you very much. Yeah, so I'm first of all, I'm Alejandro. I'm part of the applications team at EPC, and I'll be talking about especially the third article of this series. This was an effort carried out by many people at EPC, mostly involving the applications group. But yeah, I'll start with a brief summary of the work we've done. In particular, the third article is part of a series of three articles that we wrote on server power supplies. The first one, we talked about the benefits, more general overview of the benefits of multi-level topologies for AC to DC and DC to DC stages within a server power supply. In the second part, we presented a reference design for a 4-level totem pole PFC. And then in this third part, we focused on the DC to DC isolated stage, all of them using low voltage GaN. For this third part, we actually developed a fixed ratio isolated 5.5 kilowatt to 400 volt to 50 volt ISOP converter. ISOP as in input series output parallel. So the converter uses 4 LLC modules with its inputs connected in series and the outputs connected in parallel. So this means that each LLC is only exposed to 1/4 of the total input voltage, and it only processes 1/4 of the total output power. So in general, in our design, each LLC module can be used as a standalone 100 volt to 50 volt converter. And it uses a primary half bridge and a center tap full wave rectifier, where we use 150 volt GaN FETs in both the primary and the rectifier sockets. The part we chose is EPC 2305. It's rated at 150 volts, and it only has an RDS on of around 2.2 milliohm typical. It also comes in a very small package, very low profile, 3 by 5 millimeters with exposed top for efficient cooling. The magnetics are based on a planar transformer with a 1-to-1 turns ratio. and the windings built into a PCB, a very simple 8-layer PCB with only 2-ounce copper. The performance is great. We achieve peak and full load efficiencies at 98% or above, and we achieve a power density of around 600, almost 600 watts per cubic inch. And the best part is that there's still a lot of room for improvement, which we are working on right now. Another important feature that we also get asked a lot about this topology is that it has the ability to self-balance the input voltage, ensuring that when we put 400 volts across the input of the overall converter, those 400 volts are evenly shared among the 4 LLC modules. This is done by design without the need of active or additional circuits or control loops. And we also verified it through experimental results, which are provided in the article. There are many other advantages and features that I'm hoping we can discuss today.
Okay. So maybe I will ask you the first question that I've got. For the 5.5 kilowatt input series output parallel LLC converter, what practical trade-offs did you encounter between the 111 and 222 transformer variants?
Yeah. We developed 2 transformer variants for this converter. For both variants, the size of the PCB, the layer stack up, the bill of materials, the core geometry, and the core material were the same. The only difference between these 2 transformer variants were the number of turns in the primary and the secondary windings. So in the first one, we used a single turn, and in the second one, we used 2 turns, both in the primary and the secondary. So this has 2 first order consequences. The first one is, it changes the flux density across the magnetic core. With the double turn, we halve that flux density if we were to keep the same frequency. But on the other side, if we maintain the same number of layers, that means that current now has to flow twice the number of times around the transformer, which increases winding losses and conduction losses. So these two consequences manifest as a higher peak efficiency due to the lower core losses for the double turn transformer, but higher full load losses due to the conduction losses in the windings. That's the main trade-off that we encounter with these 2 transformer variants. There are some other smaller differences related to leakage inductance and magnetizing inductance. When you have more turns, you have a little bit more leakage. So we did have to adjust or make some small adjustments on the the switching frequency to account for those changes too.
Okay, thank you. And to everybody now, please feel free to submit your questions. We will be reading them in the chat. So one more question from my side. What motivated the shift from traditional 2-level topologies to cascade configurations with low voltage gallium nitride FETs?
Yeah, so this is it's a good question. For me, it's somewhat straightforward. When we think about, if we think about, for example, one of the small point of load converters where we're trying to convert from 12 volts down to core voltage. We have these little modules that can do 65 amps per phase or 50 amps per phase. And all of a sudden we start to hear that, oh, we're going to need up to 1,000 amps to power one of these GPUs. So to everyone, and no one questions this, to everyone, the obvious answer is, okay, let's multi-phase, right? We just add more phases in parallel, and that's how we scale current. So, why can't we do the same when instead of increasing current, we increase voltage? We just use one of these topologies to scale the voltage while still being able to use the same lower voltage transistors. And this has many advantages. Lower voltage GaN devices have better figure of merits than higher voltage devices, even GaN devices. And this is even after you include all the additional switches that you have to put in series when they are in a multi-level configuration or a cascade configuration. So that's straightforward answer from the point of view of the semiconductor devices. But there are other system level reasons for going for one of these topologies, especially in converters where we have a high conversion ratio. We're talking 400 volt to 50 was the prototype we designed. But we're also hearing now about 800 to 50 and 800 volt to 12. So these are 16 to 1, 64 to 1 turns ratio. When you use one of these cascaded topologies where you're also simplifying the transformer substantially. You go from needing a 64 to 1 or 16 to 1 to a 1 to 1, for example, which is what we used, or a 4 to 1. So it simplifies the design. You don't have to design a transformer to handle 5 kilowatts. You only have to do it for 1/4 of that power. You also get access to lower voltage components. Your resonant capacitors, they don't need to be rated 600 volts or they can be rated at 200 volts or even 100 volts. So, this translates to smaller components, lower profile components. You can basically improve the power density of the overall solution. The other thing is, you're not concentrating the losses in just 4 high voltage switches, but you're distributing them across a larger area, which also simplifies your cooling solution by avoiding hotspots. So there are many system level advantages to this kind of cascaded or ISOP topologies.
Okay, this all sounds very reasonable to me, but can you give an example how much space you can save compared to the other approach? How many percent space savings if I will be able to use smaller components? Very roughly.
So, well, I think I don't have a number right now because usually these what the work we've seen from other or our competitors, for example, is it's kind of integrated in their AC to DC power supply, which includes the PFC. So some of the components are kind of spread and located in a way that makes it a little bit more difficult to compare. But I think the space savings that we've seen could be around 40%. And it's not only space, but also cost.
This is a big issue, really. 40%. Yeah. Wow. But another technical question. How do multi-level and input series output parallel topologies align with emerging 800 volt DC AI server and data center architectures?
Yeah, so for the same reasons that I explained earlier, I think they would be a perfect solution for this kind of voltages, 800 volts, or there's a lot of conversation about plus minus 400 as well. So, for example, the module that we talked about in the article is 400 volt to 55.5 kilowatts using 4 modules. There's nothing that prevents connecting 4 more of these modules with their inputs in series to make up for an 800 volt bus or plus minus 400 and keep the same 50 volt output and double the output power to 11 kilowatts. And this is without any changes whatsoever to the design of the LLC modules. So it's a very nice way and simple way to scale voltage and power at the same time. And it's this concept is not limited to a 50 volt output. You can also apply it to a 12 volt output or any other output. Well, with some limitations, but it's so. For example, we've been working in the last few months on an 800 volt to 12 using the same kind of topology and input series output parallel converter using LLC modules, where we stack 8 modules in series and connect the outputs in parallel to get a 6 kilowatt isolated converter with only 8 millimeters, for example, in height. So it's I think it will be a key solution to enable the higher power densities that we're seeing in future server power supplies.
Okay, thank you very much, Alejandro. And thank you to everybody in the team who contributed to your story. We really appreciate this, and maybe we will meet at Bodo's Wide Bandgap event in early December.
I hope so.
Very good. So our next speaker would have been Lou Worm Edmonds from Navitas, but unfortunately he couldn't make it and he wasn't able to find somebody who is able to substitute him, let's say it this way. So now it's already time for Srijan Ashok from Texas Instruments. Srijan, your story was on, let me check it out, driving innovation in power supply designs with integrated TOLL packaged GaN devices. Please tell us more about the story, the solution, and everything you wanted to tell us, while all the others here will be able to type their questions. Srijan, please.
Great. I hope I'm allowed and I'm audible and visible. So yeah, thanks, I think, for the opportunity here to be able to talk about this. So yes, I think just to start talking about the reasons we went with the toll package devices, I think we have seen that there is a increasing trend around the multi-source compatible packages in the industry, considering everyone wants to secure their supply chain. So that was maybe one of the first reasons to come up with this standard package, which can be, let's say, layout compatible with the other discrete toll GaN devices that are out there. So, and on top of that, this offers you the value of integration. So TI, as you know, approaches GaN in a way that we always come up with these integrated packages with the driver and the FET in one package, just to help ease the designers, I would say, the designer's life, and also bring in some inherent benefits with relation to circuit parasitics. So since we have a good knowledge base around the driver piece, we do that. Now, coming to specifically this article, I think what we have tried to bring out in this is that the toll GaN devices, now that we have launched it, is available, or rather now that it's on TI.com, we are shortly going to launch it. It's available in a 25 milliohm onwards package, and it's can be used in multiple applications, such as server PSU. I think Alejandro was really was explaining it very nicely on how the server power is evolving, and it's going to 800 volts. So the toll will have a great role to play, the toll devices from TI, and talking about, let's say, the PFC stage in the PSU application, talking about the LLC primary, which uses 650 volts, or even 800 volt designs, where this device can be used in a 3-level topology to deliver the 800 volt primary to whatever voltage in the secondary that we decide upon. I think there are multiple voltages floating around, 48 volts, 12 volts, etc. So yeah, that's one application. There's definitely other important areas that the toll devices can have a play, such as the energy infrastructure, more specifically talking about solar microinverters. And I would say in that there are multiple topologies also that are there, like LLC cycloconverters. So on the high voltage side, this can definitely play a role. Then apart from that, there can also be applications in the automotive space, in the chargers, etc. We see that both two-wheeler, three-wheeler, and four-wheeler, I think, depending upon which part of the world you are, I think one or the other of the EVs, or maybe more of them also, is very popular. So in the entire charging infrastructure, I think this device will have a role to play in the AC to DC conversion to create the charging voltages for the batteries. And then, yeah, there is also a very growing adoption of GaN in appliance power supplies, more specifically like TV power supplies, etc., where the TVs are becoming even thinner and thinner by the day. And the idea is to have like a very I would say a very uh, high density power supply to manage that reduction in the panel thickness. So I think that again is where toll will have a role to play in doing the AC to DC conversion for the panel power and powering up other peripherals within the TV. So that's just TV is just one example, but there are even in other appliances you are seeing that there is an increasing penetration of GaN, and I think yeah, toll device with a different RDS ons. We have 25, 35, 70 milliohm, which will help in getting there with the different power supply. So I think that was the article. I think that's a very quick summary. And yeah, happy to take any questions there. Yeah.
Okay, so now we are looking for questions in the chat. Please feel free to ask whatever you wanted to know. In the meantime, Srijan, maybe you can tell us a little bit more about the PCB layout. In which way does the PCB layout change by using devices?
Yeah. So when you take these devices, I think we have the driver integrated with a lot of protection features and some smart switching features as well. So depending upon the topology that you use, you may use a zero voltage detection or a zero current detection. So that if you are using, let's say, a discrete FET with a discrete driver, you will need some external mechanism to do that detection. Now with our toll devices, all that comes as part of the, I would say, part of the device itself, because we integrate the ZVD, ZCD detection. Additionally, if you want to implement like protection features such as overcurrent, over temperature protection, again, that comes integrated with the toll GaN devices. So all these integration, what it helps with is basically reduce your PCB. I would say the extra components that you put around the PCB to do all this sensing and protection and, let's say, control-based sensing, all that kind of becomes simplified, and you can actually do a very high density layout and a very simple layout, and also avoid the gate loop parasitics. That's again a major challenge with some of the layouts that we have dealt with on discrete side. So when you're switching at a high frequency, so I think that also kind of gets taken care of here. Yeah.
In your story, you do not only mention the TV power supplies that you already talked about, but you also spoke about solar microinverters.
Yes. Okay.
Especially considering the single or double panel devices that you can put onto your balcony, which are becoming more and more popular, at least in Germany.
Yeah.
Maybe it would be interesting to hear a little bit more about that kind of application.
Yes. So definitely, I think microinverter is basically, if I have to just give a very high level summary, and Alfred, you did a great job in telling that, I think it's becoming increasingly popular to have your own local panels when it comes to households having them. And microinverters is a way of consuming that local power at your home itself. You don't need to, or rather, most of the microinverters we deal with, they don't have a feedback to the grid. You just consume the power at your household. Now, there are two topologies that we see specifically in that. One is a two-stage topology where you have the first stage LLC conversion from the panel voltage, which is typically a low voltage, 75 volts, so depending upon what's the panel configuration, going up to, let's say, a 400 volt. And typically it uses toll on the secondary side of the LLC because that's where the high voltage is. And then there is an inverter stage, which is basically also uses toll to invert that voltage into a usable AC, which then can be used by the appliances, various appliances in your house. So that's one topology. The other topology is cycloconverter, which is more like a single stage, again uses a transformer, but it doesn't have an LLC plus PFC. It is just like a single stage topology, which does the conversion from DC directly to the usable AC at home. So depending upon what's the both topologies have their pros and cons, and depending upon what's the preference of the customer, they end up using one or the other. Yeah.
You can have the best efficiency in the world, but you will still have some losses. And the lower the losses, the better it is, of course. But when it comes to your toll devices, please tell us a little bit more about how to get the heat off. How does it work over there? Do we need forced cooling, or where are the boundaries of using forced cooling or not?
Absolutely. So this being toll is a bottom side cool device. So we have a extended I would say a pad on the bottom side of the device, and that can be attached onto the PCB, which typically what we have seen the cooling mechanisms that our customers end up using, because this is already in many active designs. They will have a heat sink attached to the back of the PCB, and the PCB can have a high copper density and with thermal vias, which can take the heat from the side that the toll is soldered, the device is soldered on, to the other side where all the cooling mechanisms, let's say the heat sink and if air cooling is also valid. So I just told you that this is getting used in solar applications. So typically solar appliances, they don't have and if you even have a TV at home, you would see that there is no fan-based cooling there. It's mostly uh, non-active or passive cooling that we do. So our packages enable a very good R theta J, which is the thermal resistance, which essentially ensures that the heat is effectively taken out from the package. And if you have a good cooling mechanism, be it active, passive. So in server power supplies, you see that there is a lot of fans, liquid cooling, etc. So be it that kind of mechanism, or let's say a appliance or solar microinverter kind of mechanism where there is no active cooling. I think these devices work well in both. It's just that you have to then design according to what infrastructure you have available in your end equipment. Yeah. I'm
Sorry.
unable to.
Thank you very much. Are there any questions that you want to ask? This is your last chance. Srijan is here to answer them. This is the voice in the desert calling, I think. No, but thank you very much, Srijan, for explaining everything.
Yeah.
And
thank you.
I'd like
It's
to
a pleasure. Yeah.
Thank you, gentlemen. And also thank you, ladies. We are looking forward to see you all again in December on our wideband gap conference in the Hilton in Munich at the airport. So for now, I hope you will have a nice afternoon and relax. So far, goodbye, friends.
Bye-bye. Thank you.
Bye-bye. Thanks.
Bye. Thank
Thank
you.
you.
Have a nice one. Yeah.